Hey, flipped chemistry, how you doing? We're going to be jumping into another lecture here, continuing our conversation of gases. Now we're looking at stoichiometry in gases, or gases and moles. Not that kind of gassing a mole, although, that's effective too. No, we're looking at how to get stoichiometry information out of the number of liters of gas you had at what temperature and things of that nature. So at a constant temperature and pressure, 1 mole of any gas, doesn't matter which one, occupies 22.4 liters of space. So that's really helpful. The size of the molecule does not matter when it comes to how much room a gas takes up. And that's because so little of the space that a gas takes up is actually the matter. Most of it is just space for the things to travel around. And so the actual molecule size matters not at all. The gas takes up as much room as it does based on how many moles of gas particles there are and the amount of kinetic energy present, which is determined by temperature and things like that. So this allows you to calculate the number of moles of a gas at its current temperature, pressure, and volume. If we have a non-standard condition, then we have to turn those to standard conditions first, okay? So what is standard condition? We should say that out loud. Standard conditions is 1 atmosphere of pressure, which is also 760 torr. You could look up equivalent pressure readings, but it's 1 atmosphere of pressure, and then 0 degrees Celsius, or 273 Kelvin, etc. So we need to turn gases at some other condition into standard temperature and pressure, and then once we have that, we can use their volume to calculate how many moles there are. Let's look at several examples. This is my picture of my old scuba cylinder. This is a steel 90. It's what I used to dive with when I was diving all the time in California. Now I live in Hawaii and I don't go diving. I don't understand. Nobody here likes to dive. They're all like, oh, real people hold their breath, whatever. Anyway, here we are, scuba cylinder, compressed gas at 20 degrees Celsius, and 1.55 times 10 to the 5th torr, or in PSI, that's 3,000 PSI. This gas occupies a volume of 90 liters. So it's 90 liters inside that cylinder. And how many moles of gas particles are there? I want to know how many actual pieces of gas there are in that cylinder. Well, I need to adjust those extreme conditions. 10 to the 5th torr is a lot of pressure. I need to let that go out to standard atmospheric pressure and 0 degrees Celsius and see what the volume does. So let's use the combined gas law first, okay? P1, V1, T1, P2, V2, T2. Let's put in everything we know. So I'm at 1.55 times 10 to the 5th torr and 90 liters of volume, and the temperature is 20 Celsius or 293 Kelvin. I'm going to be going to 760 torr, and I'm going to be going to 273 Kelvin. I need to get to this unknown pressure. So we're going to use this law, and we're going to do all the math on one side, and that comes up to 47,610.9. That's what all of these numbers times and divided by each other are, okay? And then over here, I need to do a little bit of algebra to figure out what this is. So there's my number for all of this, and then 760 times the unknown volume divided by 273K is going to be what I have over here. So let's get the 273 over to that side, and then let's divide by the 760. And solving for V, I have very large number, 17,102.33. That's my new volume. So if I were to take all the air in this cylinder and reduce the pressure and and the temperature and let it go to STP, I'm going to wind up with 17,000 liters of air instead of 90 liters of air. You can see what the difference makes there. It's incredible. So I put that back in, and now that I know what the volume is at STP, I can figure out how many moles there are. At STP, every gas has a molar volume of 22.4 liters, so 17,102.33 liters, 22.4 liters. The liters are going to cancel, and I'm going to figure out that I do, in fact, have 763.496875 moles of gas in this cylinder. Correct for significant digits real quick. And 760 moles of gas, because I only have at worst, I have 2 significant digits. Oh, look, there's no decimal point. Should have been. 2 significant digits, 760 moles of gas. Okay. Now, I can also use this to determine density. Density is mass divided by volume, in this case grams per liter, and every gas has the same number of liters per mole or moles per liter. So for densities of gases, it's only the mass of the gas. That's all that's going to affect the density, right? Because the volume will always be the same. So we measure grams per liter at STP, and that's what we record for the density of a gas. Here's a cool little example of this. He's filling up this chamber with sulfur hexafluoride. Okay? It's just a very dense gas. So the gas is sitting in here. It's not going out. And then a tinfoil boat can float on the gas. Pretty cool. And then he can dip the gas out with a beaker and pour it in the tinfoil boat because the gas is heavier than air and it's staying in here. And here you can see how gases are basically just less dense fluids, but they can behave like a fluid. They do behave like a fluid. All right. An ideal gas is one that perfectly obeys the kinetic molecular model. No gas is completely ideal, but most are close enough that the model works. It's workable. So a gas gets in, if it gets into very high pressures or very low temperatures, then it stops behaving like an ideal gas. But the equation I'm about to show you, the ideal gas law, is the mother gas law equation. You can use it to calculate anything about a gas, and so it's very, very, very useful. You see that pressure, volume, and temperature are still involved. Temperature, remember, used to be underneath this. PV over T was the combined gas law. Now we've removed the temperature from the denominator. We've moved it over here onto this side of the equation, and we've added to this a constant value for R. And R is different things depending on the units of measurement. You'll have to look up what R is. You don't need to memorize all the values for R. I don't hate you. N is the number of moles of gas. So pressure, volume, number of moles of gas, the constant, and then temperature. And if you know, if you know 3 of these, you can find out the 4th, and you can calculate all kinds of different changes based on this. So it's a really cool equation. You will use it a whole lot, and if you have a hard time remembering it, PV equals nRT, you can just think of what it sounds like, Pvnert, and remember the Pvnert equation, okay? The PV equals nRT, it's a funny sounding word, and that's how I always remembered it. The ideal gas constant changes based on which units are used. Don't memorize these. Just know that they are there. Anytime I ask you to do an ideal gas law, I will give you the value for R appropriate to its measurements. But just as an example, for atmospheres and liters, R equals this. For torrs and liters, R equals this. For pascals and cubic meters, R equals this. And there's tons more combinations. R has, like, I don't know, 50 values or more. So don't memorize R. Just know that you need to look it up and put it in the equation. All right. Here's an example of an ideal gas law equation. 300 exactly moles of helium gas are put into a weather balloon at sea level, which is 1 atmosphere. And underneath my picture it says, on a warm summer day. 30 degrees Celsius, that's pretty warm. And that would be 303 Kelvin. Okay, so what's the volume in cubic meters at launch? We're going to use the ideal gas law to answer that question. Then we're going to use the combined gas law to figure out what it will be when it gets to altitude and the pressure has dropped to 0.2609 atmospheres and the temperature has dropped to -35 Celsius or 238 Kelvin. Okay, let's take a look at it. So first we're going to use the ideal gas law, and we're going to get the volume at the initial condition, right? So we need to look up the right value for R. I have temperature in Kelvin, I have volume in cubic meters, and I have pressure in atmospheres. So if I'm using those units, R is 0.0821, okay? And so PV, pressure, volume is what I don't know. N, 300 moles, R, 0.0821, T, 303 Kelvin. Multiply it all together and then divide across, right? So I'm going to get that my volume is 7,462.89 liters at sea level. So that's a big balloon, right? 7,462.89 liters. So that's a lot of air in there. That's at launch. I need to make sure that I correct for sig figs. I have 3, 3, 3, 2. Okay, so 7,500 liters at launch. Then it goes up into the atmosphere, right? I am going to have the new situation of 0.2609 atmospheres, unknown volume, 300 moles still, same value for R, new temperature. Now I could have used the combined gas law to do this as well, but I just want to show you how ideal gas law works as well. So multiply across everything I know to solve for V. V is 22,468.1 liters. That's a much, much, much bigger balloon, right? Correct for sig figs, 22,000 liters at its altitude. So the balloon nearly triples in size as it launches from 7,500 to 22,000 liters in volume. And that's typical of weather balloons. That's why they never look very full when they're launched, because when they get to altitude, they are much larger than they otherwise would be, okay? And then, weather balloons are not just for weather. People are also being launched in them as well. And you can buy rides to the edge of space in a helium balloon and then glide down on a paraglider. It's pretty awesome. It's incredibly expensive. I'll never do it. But, it's happening. You can ride in capsules very, 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 very high in the atmosphere and see the curvature of the Earth and all that kind of cool stuff. So weather balloons are awesome. And all of these gas laws help you unlock what's going on. If you have any questions, let me know, and I'll be happy to answer them. Put them in the comments field below, or I'll see you tomorrow in class, and we'll just keep rocking through chemistry. Jesus loves you, and so do I. See you tomorrow.